The chart that you see in the key question number 2 is one of many charts that you'll be using to compare the relative acidity of various groups. In this chart, we will be drawing out the conjugate base, and we'll be exploring the atom effect and the resonance effect. In future problems, we'll also be looking at stabilization by induction, as well as the orbital effect. I've set up these charts so that the comparisons between the conjugate bases and their relative stabilities will be more straightforward for you, and then you can very clearly make a conclusion about the relative acidity of the conjugate acid. So starting off in the first 2 rows, we're actually talking about only one molecule, but we're talking about 2 parts of that one molecule. So part 1 is the amine, part 2 is the amide. So we're comparing the relative acidity of an amine versus an amide. To make it easier to refer to these different groups, I'm going to label it in this way. So we can talk about the acid 1 and the acid 2. Acid 1 is the amine, acid 2 is the amide. And then we can draw the corresponding conjugate bases. Now sometimes you'll also be wanting to draw resonance forms. So to make this a little bit easier, one of the strategies that I ask you to do, especially for larger molecules, is we can abbreviate part of the molecule as R. So let us say I'm focusing on the proton that's on the nitrogen labeled number 1, then the rest of the group can just be called R. So I'm going to, in a sense, refer to the rest of the group by writing a big R on the top. So the corresponding conjugate base would look like this. And there we've just focused, therefore, on the important features of that conjugate base. It's a negative charge on the nitrogen. In turn, I can then label the rest of this group as R, and then just focus on the amide functional group and its corresponding conjugate base. So if I write R, and as I was starting to write, I realized that I want to save a little bit of room so I can draw a resonance form. So I draw in most of the amide functional group, but I take off that one proton and I put a negative charge on the nitrogen. So far, the 2 conjugate bases look quite similar. There's a negative charge on the nitrogen in both cases. But hopefully, again, you recognize that the lone pair there is an allelic lone pair. So I can draw a resonance form. In drawing the resonance form, I see that the negative charge can also sit on the oxygen. And of course, we have a pi bond there. So to complete the analysis, I'm going to look at the atom effect. I notice that both of the conjugate bases have a negative charge on a nitrogen. So when we refer to the atom effect, it's really helpful to actually specify what's happening. So negative charge on a nitrogen. But notice that we also need to account for the fact that there's resonance happening in conjugate base number 2. And as such, it impacts the atom effect. So not only is there a negative charge on a nitrogen in case of conjugate base number 2, there's also a negative charge on the oxygen. So by completing this chart, I'm making quite explicit what's happening with these conjugate bases. The R is inquiring whether or not there's any stabilization by resonance for the conjugate base. So there's no stabilization for conjugate base number 1, and there is stabilization by resonance for conjugate base 2. As mentioned, we will talk about stabilization by induction and the orbital effect next time. So therefore, if I want to make a conclusion, I'm going to tie together the various things that I have highlighted in completing this chart. So I might make a statement like this. The conjugate base number 2 has a better atom effect, and that's of course as the result of the resonance, because it has a negative charge on the oxygen and the nitrogen versus just nitrogen alone. And it also has stabilization by resonance. So in fact, there's 2 things going on there. Notice that I abbreviate the stabilization by resonance by writing S by R, and that's perfectly fine. So most importantly, I make these conclusions about the conjugate base number 2, but then I make a conclusion about the conjugate acid number 2. So conjugate base 2 is more stabilized, therefore the conjugate acid 2 is a stronger acid. Let's go through the exercise, therefore, for the next set of groups that we're comparing. Again, it's one molecule, but I'm comparing the proton that's on a carboxylic acid and a proton that's found on an amide. So once again, I'm going to label 1 and 2. I'm going to label the rest of the molecule as R. I'm going to draw the conjugate base for proton 1, labeled 1. So the rest of this is R. I have a negative charge on that oxygen. And as you might imagine, of course, it does have a resonance form where the negative charge sits on the other oxygen. So indeed, there's stabilization by resonance. I can, in case of the proton label number 2, call the rest of the group R. And now I write out R and focus on the fact that there's a negative charge on this nitrogen. I've got my carbonyl group. So now I draw in the resonance form. And as you might imagine, instead of the negative charge sitting on the nitrogen, it's going to sit on the oxygen. So now using this information to complete the A and the R component of my chart, in terms of the atom effect for conjugate base 1, I have a negative charge on an oxygen, and I have another negative charge on an oxygen. I list the two, and in a sense that goes hand in hand with the fact that there is stabilization by resonance. In the case of the conjugate base number 2, there's also stabilization by resonance. But in terms of the atom effect, I have a negative charge on a nitrogen, and I have a negative charge on an oxygen. So while both conjugate bases have stabilization by resonance, I would pinpoint that one conjugate base is going to be more stabilized, and this is due to the atom effect. And this is conjugate base number 1, because the negative charge resides entirely on oxygens, and oxygens are more electronegative than a nitrogen. So it's not so much the difference in resonance, it's a difference in the atom effect. To put this into words, it would go something like this. Although both conjugate bases have stabilization by resonance, conjugate base 1 has a better atom effect. Again, 2 oxygens with a negative charge versus 1 oxygen and 1 nitrogen. And then I turn my attention to the conjugate acid, and I say the conjugate acid one is a stronger acid. So again, any of the stabilization statements, it's about the negatively charged conjugate base. And then the final conclusion is about the relative strength of the conjugate acid. I'm hoping that by repeating these patterns and by repeating the focus, you too will be looking at to what degree is the negatively charged conjugate base stabilized. Look at the factors, the atom effect, resonance, and then make a conclusion about the relative acidity of the conjugate acid. In the next part of our Chem Activity 14, so part 2, we will look at stabilization by induction and the orbital effect and tie all of these factors together.